In 2019, a gamma-ray afterglow appeared with no galaxy around. A fading ember glowed where no parent star seemed alive. Here is the immediate takeaway, right up front. Some cosmic events erase their return address by design. Beams miss us, debris drifts, while maps smear sources across space. We still can read the scorch marks and rebuild partial stories. Tonight, we chase signals that refuse to name their home. You will see how physics turns origins into ghosts. You step into a dark room and only the smoke remains. That scene matches an orphan afterglow, a fading blaze without a clear parent. An orphan afterglow is dying light from a gamma-ray burst. We see it off-axis or behind dust. It matters because these misaligned flares hide stellar deaths across the universe. Narrow jets sweep space like laser pointers, while most directions see little. If you sit off the beam, you catch only embers. Dust can muffle the host galaxy, while distance drains signal. Telescopes then see a lonely fade without an obvious birthplace. Example in real terms to ground this in data. GRB 70,125 looked hostless at first, despite deep imaging. Later work found a faint galaxy, almost lost in background glare. The burst likely fired a narrow jet that never aimed at us. We saw the sideways afterglow, not the blinding gamma flash. Numbers help here because scale anchors the picture. Typical jet openings are a few degrees wide. Miss by 10 degrees and the bright beam vanishes from view. The afterglow expands, cools, and shifts into radio and optical. Weeks pass and the field looks normal again. Net result, the parent event happened, yet its home hides in geometry. A particle slams into the upper atmosphere and a shower blooms. That cascade echoes an older journey, started beyond our galaxy. Ultra-high-energy cosmic rays are charged nuclei with extreme energies. We care because their energies beat human accelerators by orders of magnitude. Magnetic fields twist their paths like wind bending a smoke trail. The sky map blurs, so the source location becomes guesswork. Even worse, the universe trims their energy during travel. Interactions with background light sap momentum over millions of light years. The most extreme events hit about 10 to the 20 electron volts. That is like a fast-pitched baseball compressed into a proton. Detectors watch for blue flashes in air or ground particle splats. Arrays stitch directions and energies, then compare with nearby galaxies. Sometimes hints appear near starburst regions, rich with powerful winds. Yet each candidate faces doubt because deflection scrambles arrival angles. Rule of thumb, the higher the charge, the bigger the bend. So iron hides its birthplace better than a lone proton. Time also muddies origins because sources flare and fade unpredictably. By the time the shower arrives, the canon may be quiet. Bottom line, the path is a maze, so the origin stays fuzzy. A lone planet drifts under starlight with no sun to warm it. That wanderer captures the idea of a rogue planet. A rogue planet is a world ejected from its birth system. You should care because many planets may live unbound between stars. Gravity kicks them out during chaotic early dances with giants. Close encounters trade energy, so small worlds escape at high speed. Cluster flybys add nudges, while young disks stir orbital instabilities. Over time, the unlucky few become the galaxy's homeless travelers. Here is a practical picture so you can see it. Microlensing surveys catch brief brightening as a hidden mass passes. The signal lasts hours or days, then vanishes forever. Some events suggest Jupiter masses, roaming without any visible star. Extrapolations imply billions of free floaters in the Milky Way. Young planets glow from heat, so infrared cameras can sometimes spot them. But distance and dust dim that glow below current limits. Life prospects change too, since warmth must come from within. Tidal heating or radioactivity might keep pockets barely habitable. Still, sunlight is gone, so surfaces freeze into deep night. So the picture is, ejections are common, and origins get erased. A crisp radio ping arrives, lasting milliseconds, then it is gone. That is the feeling of a fast radio burst, or FRB. An FRB is a super bright radio flash from far away. It matters because FRBs probe gas between galaxies, like sonar pings. Dispersion stretches low frequencies because electrons delay the radio wave. The stretch size, called dispersion measure, estimates distance through intervening plasma. Mechanically, you need precise timing and location across many antennas. Interferometers pinpoint sources, while dishes catch strength and frequency sweep. Example in real terms, a pair that shows the range of hosts. FRB 121,102 repeats from a tiny star-forming dwarf galaxy. FRB 190,523 came once from a more massive galaxy halo. Yet many bursts remain unlocalized, with no clear host in sight. The culprit is speed, because milliseconds leave little room for triggers. Small arrays cannot triangulate fast enough before the ping fades. Common mistake is to assume every FRB has a bright host. Some likely live in faint dwarfs below survey detection thresholds. Others may sit far out in halos, away from starlight. So the map is soft, even if the flash is sharp. A ghost particle crosses Earth straight through rock without slowing down. That line evokes a high-energy neutrino, born in violent cosmic engines. A neutrino is nearly massless, neutral, and feebly interacting with matter. We care because neutrinos fly straight, preserving direction from distant sources. Detectors wait in ice or water, watching for rare blue flashes. Cherenkov light marks a passing muon, created by a neutrino strike. The direction is reconstructed, though with degree-scale uncertainty for many events. Then astronomers search the sky region, hoping for an active culprit. One famous case linked a neutrino with a flaring blazar. Most events lack matches because flares end before alerts spread. Time also hurts, since tidal disruption flares fade within days. Dust can hide weak afterglows, especially in crowded galactic planes. The net effect is a quiet sky after a loud whisper. Numbers help here to set expectations for patience. A cubic kilometer detector may catch dozens yearly. Each carries precious direction, but little extra context beyond energy. Pile enough together and patterns may finally emerge. For now, origins remain hidden by weak signals and late lookups. Bottom line, neutrinos promise clean arrows, yet leave few clear homes. Two black holes circle tighter, then collide, shaking spacetime like water. That motion embodies a merger that glows in gravity, not light. A stellar mass black hole merger is dark electromagnetically by default. This matters because we detect the waves, yet rarely see the scene. The wave encodes masses, spins, and distance across its chirping arc. Sky localization is coarse, spanning hundreds of square degrees at first. No gas means no fireworks, so telescopes find no counterpart. If disks or stars remain, faint light may appear later. Example in real terms, our first loud signal in 2015. G150,914 was our first solid detection, with no light found. Many later events look similar, within larger positional error regions. Neutron star mergers can shine, spraying our process elements into space. But black hole pairs usually swallow clean, then drift into quiet. Host environments are debated, from star clusters to galactic disks. Kicks from previous supernovae can move binaries far from birth. By merger time, the system may sit in thin intergalactic space. Even a successful detection leaves the origin story incomplete. What to remember, gravity tells us who collided, not where they lived. A dim shard streaks past the sun, on a steep hyperbolic path. That visitor captures an interstellar object passing through on a brief tour. An interstellar object is debris from another system, ejected long ago. We care because it samples alien building blocks without a spacecraft. The flyby is quick, while sunlight alters surface gases and motion. Outgassing can push slightly, creating small non-gravitational accelerations. Shape and spin confuse models, since reflections change with every turn. Measurements lag behind because discovery often comes after closest approach. Concrete examples help because numbers beat hand waving. One ʻOumuamua glowed reddish with an elongated shape estimate. It showed gentle acceleration, consistent with outgassing or surface release. 2I Borisov looked comet-like, with a classic dust tail and coma. Its chemistry seemed familiar, matching many solar system comets. Neither object revealed a clear birthplace beyond a broad incoming direction. The sky contains countless stars, so backtracking spreads over many options. Future intercept missions could sample surfaces before heat scrambles clues. Until then, each visitor keeps the return address vague on purpose. Net result, brief encounters limit tracing, so origins remain broad. A galaxy wears faint ribbons, like ghostly rivers circling its halo. Those ribbons picture tidal streams, the shreds of swallowed companions. A tidal stream is a long arc of stars, stripped by gravity. It matters because streams remember orbits long after dwarfs dissolve. Gravity stretches the smaller galaxy while stars peel off near pericenter. The debris wraps the host, forming loops, shells, and feathered plumes. Simulations match these shapes, revealing merger times and original masses, but the core remnant can vanish below surface brightness limits. Here is a grounding example from the skies you can recognize. The Milky Way shows the giant Sagittarius stream across the sky. Other arcs, like GD-1, carry gaps, perhaps carved by dense clumps. Around Andromeda, deep imaging reveals a sprawling shelf of debris. Many halos host shells, yet the parent dwarf is missing. Detection bias plays a role, since faint cores fade fastest. Background light from the host also washes subtle knots away. By the time we look, the culprit has blended into the glow. Careful star counts can still tease out hidden overdensities. Bottom line, the shapes survive, while the original home dissolves. So many signals, yet so few clean return addresses. Now it makes sense. Geometry, distance, and time can erase origins before we even look. Some paths twist, some beams miss, while others simply fade away. The practical takeaway is simple: chase the imprint, not the headline. Multi-messenger campaigns help because neutrinos, waves, and light cross-check. Wider arrays react faster, so milliseconds do not slip past. Deeper surveys reveal faint hosts hiding under glare and dust. The picture is hopeful, even if cosmic mail arrives unmarked. If this sparked a new question, leave it below. I read them. Subscribe if you want more clear stories without the fluff.